Good evening, everyone. In the last class, we discussed about the Gauss law, and we discussed how the electric flux only depends through a closed surface depends only on the charge enclosed within the closed surface, right? Does not depend upon the charge outside the closed surface. So we'll be continuing with the same, and we'll be also discussing with the applications of the Gauss law, right? So before discussing the applications of the Gauss law, we'll try to solve this problem here on the screen. The problem is that electric field has been given along the x direction. That's 5 root x. So electric field is given as a function of x, as a function of position along x. And the Ey and the Ez component of the electric field is 0, means electric field is totally directed along the x direction. Then we have to find the net flux through the cube, right? Net flux through the cube and the net charge enclosed by the cube, right? So in this case, you can see the cube has been placed at a distance of 1 meter from the origin of this Cartesian system, right? And electric field is also directed along the positive x-axis, right? So the electric field will be directed like this, right? And we can clearly see that it's a non-uniform electric field because the electric field strength depends upon the x here, right? It's a function of x, so it's not a uniform electric field, it's a non-uniform electric field, right? So electric field line will be entering through this surface of this cube and they will be leaving through this surface of this cube, right? So the electric field line enter this surface, right, on the front. The electric field leave the surface at the back, right? And we know that there are six surfaces for the cube, right? Six sides of the cube, and we can say that only through these two surfaces the electric field will be passing. So flux will be only associated with these two surfaces, right? And for rest of the four surfaces, the electric field will be 0 because all those surfaces will be directed either along z direction or along y direction. So the electric flux through all those surfaces, which is the electric flux through all those sides which are directed along y or z direction will be 0 because there will be no electric field, no component of electric field along y and z direction, right? So if we calculate the electric flux because of through this surface here, through this surface, if we calculate the electric flux through this surface, right? And we know the magnitude of electric flux is dependent upon the position x, right? And this surface is placed at a distance of a is equal to 1 meter, right? It's placed at a distance of a is equal to 1 meter. So at this point, the electric field strength will be nothing. It will be 5 root 1. That's equal to 5 volt per meter, right? That will be volt per meter, correct? So this will be the electric field strength, correct? So at this surface, at the surface which is at the back, right, the electric field strength will now change. It will be a different electric field strength at this point. And we know that this side will be now at a distance of uh, a, that's 1 meter, and there will be one more distance, that's the side of this cube, that's 1 meter again. So this is at a distance of x is equal to 2 meters, right? So for this point, electric field will be nothing. It will be 5 root 2, right? It will be 5 root 2 volt per meter, right? So the total electric flux, we can use the Gauss law for this surface. It will be integral of E dot ds, right? To the closed surface, that's equal to Q enclosed upon the epsilon naught. And it's not given that what is the charge enclosed, right? If their total flux is non-zero, then there must be some charge enclosed within this closed surface, right? So we'll calculate this. Let me call this surface, if this is surface 1, let me call this S1, and let me call this surface here as S2. So the flux through, the total flux through this cube will be nothing. It will be a phi S1 plus phi S2. That will be the total flux enclosed through this cube, right? That will be equal to Q enclosed upon epsilon naught, right? Q enclosed upon epsilon naught. And the flux through this side will be nothing. It will be E dot S1. We can write it as E1 S1 plus E dot S2, right? that will be equal to Q enclosed, correct? Or we can say this total flux will be equal to, and we can say that for the first side, the angle between the S vector and the E vector is 180 degrees. So the electric field will be, electric flux will be nothing. It will be E1 S1 minus E1 S1. And then for the second side, through which the electric flux is moving out, the direction of the area vector is along the direction of the electric field. So it will be E2S2, right? Angle between the surface and the electric field will be 0 degrees. So it will be E2S2. So the net electric flux will be nothing. Phi net, that is minus E1 is 5 and S1 is the surface area of this cube. So it will be 1 square, that's 1 square plus 5 root 2 into 1 square, right? So it will be overall 5 root 2 minus 1 will be the total flux, right? This will be the total flux through this cube. And we know that total flux is nothing. Phi total, phi net is nothing, that's Q enclosed upon epsilon naught, right? For our Q enclosed, charge enclosed will be epsilon naught times flux. So it will be epsilon naught, pi epsilon naught under root of root 2 minus 1. So this will be the charge enclosed within this cube, which is responsible for this total flux, right? So that was it with respect to this question. That's how we calculate the charge enclosed if we know the electric flux passing through the closed surface, right? Now, important point about Gauss law is the applications of the Gauss law, right? Let's suppose that we define Gauss law as that's integral of E dot ds means the total flux through the closed surface is nothing, it's the charge enclosed upon the epsilon naught, right? It's the charge enclosed upon the epsilon naught. And suppose that charge enclosed is equal to 0, right? Charge enclosed is equal to 0. If charge enclosed is 0, it means that the total flux through the closed surface will be equal to 0, right? That's equal to 5. So 5 will be total, 5 will be equal to 0. It means that the closed integral of electric field vector with respect to the surface, right? E dot integral of E dot ds will be 0. But it's not necessary that this electric field will also be 0, right? This electric field can be non-zero, right? It's not necessary that even if the total flux through the closed surface is 0, it's not necessary that the electric field is also 0. Let me give a simple example for this. Let's suppose that we have this sphere, right? It's a closed surface, and I'm placing two charges. I'm placing two charges, Q and minus Q within this sphere, right? Q and minus Q within this sphere. And let me suppose that uh, I I choose a point P here. This is the point P, and we know that for this sphere, the total charge enclosed is nothing. It's Q minus Q. That's 0, right? That's equal to 0. Or we can say the total flux through this sphere will be equal to 0, correct? It will be 0. But if we calculate the electric field at this point P because of this positive charge and negative charge, the field because of this positive charge will be directed away from this positive charge in this direction, right? And electric field because of this negative charge will be towards this negative charge, right, in this direction. And there will be definitely some net electric field along this direction, right? So it means that if this is E1, if this is E2, right, then this electric field is going to be E1 vector plus E2 vector, right? And this is a non-zero electric field, right? It's a non-zero electric field. So in this case, here we can see that even if the flux through the surface is 0, the total electric flux is 0, but still there is some net electric field within this closed surface. So we cannot say that even if the flux is 0, if the charge enclosed is 0, it doesn't mean the electric field total charge enclosed is 0, it doesn't mean the electric field within the closed surface is 0. So it may be 0, it may not be 0, right? So it will be 0 in only three cases, right? It will be 0 in only if there's if the charge distribution is symmetric, right? It will be 0 in three symmetric cases. So if Q enclosed is 0, then electric field will be 0 in three symmetric cases only. in three symmetric cases only, right? In three symmetric cases only, the electric field will be zero when the charge enclosed is zero, right? Let's suppose that in a closed surface, we're talking about the closed surfaces, right? The first symmetry is the spherical symmetry, right? Another is the cylindrical symmetry. Another is the cylindrical symmetry, right? And the third one is plane symmetry. So in these three cases only, if the charge enclosed is zero, then the electric field will also be zero, right? Otherwise, the electric field will be non-zero, right? And only in these three symmetric cases, we apply the Gauss law, right? To calculate the electric field, due to the charge distribution, right? So suppose if in these cases the electric field is symmetric, it means that the electric field intensity will have the same magnitude at every point on the Gaussian surface. It means that magnitude of magnitude of electric field will be same on Gaussian surface, right? Magnitude of electric field will be same on Gaussian surface. Let's talk about the spherical symmetry. Let's suppose this is a sphere here. We have a sphere here, right? This is a sphere here. And let me draw a Gaussian surface, right? Within this sphere. Let's suppose this is a Gaussian surface, right? This surface is a Gaussian surface, right? It's a Gaussian surface. And let's suppose that if the electric field is present there, on this Gaussian surface, let's suppose this is center, right? Then the electric field on the sphere will be directed radially outwards like this, in this direction, right? And this will be the electric flux through this Gaussian surface, right? The direction of the electric field vector on the Gaussian surface can be different, right? It can be different. The direction of electric field vector on Gaussian surface will be different, right? But the magnitude on each and every point on the Gaussian surface will be same, right? And here in the case of spherical symmetry, the electric field is directed along the radius, right? For the positive charge, it's directed along the radius away from the center, right? And let's suppose some electric field does exist, right? Some electric field does exist. So let me denote this direction as r cap direction, right? Denote this direction as r cap direction, right? So let's suppose that electric field does exist on this Gaussian surface, but we know that it's given that the charge enclosed here is zero. Charge enclosed here is zero. Charge enclosed here is zero. So if we apply this Gaussian law on this Gaussian surface, that's integral of E dot ds, right? And this is the direction of the electric field vector, right? Here in this case, the direction of the electric field vector is the same as the direction of this Gaussian surface, right? So we can say that integral of ER vector dot ds. ds is also having the direction of r cap, right? So r cap dot r cap will be equal to what? So we'll be left with integral of eds, right? Integral of eds. Integral of eds. That will be equal to charge enclosed upon the epsilon naught. And we know it's given that the charge enclosed is zero. And E is constant here because on the Gaussian surface we said that the magnitude of the electric field vector is same. It's a constant. So integral of E ds, it will be equal to 0, right? So from here we can clearly see that the electric field vector or the magnitude of the electric field here is 0 only in the symmetric case. It means that it's only 0. It's only 0 when the electric field is having the same magnitude on at every point on the Gaussian surface, right? So it's not always possible that if the total charge enclosed is 0, then the electric field vector will also be 0. It's only possible when there is a case of symmetry, right? Here we discuss the case of spherical symmetry, right? So let's try to apply Gauss law on different symmetrical cases, right? Let's discuss electric field due to hollow sphere, right? Electric field due to hollow sphere. We'll try to calculate the electric field due to hollow sphere inside as well as outside this sphere, right? Let's suppose that we have a hollow sphere here. This is our hollow sphere, right? So the radius of this hollow sphere is nothing, it's equal to R, capital R, right? And let's suppose that the charge plus Q is uniformly distributed, right? It's uniformly distributed on the surface of the sphere, right? Uniformly distributed charge, right? Right? Uniformly distributed charge. And we want to calculate the electric field inside this hollow sphere, right? We want to calculate the electric field intensity inside this hollow sphere, right? So what we'll be doing is that we'll be applying the Gauss law, right? We'll choose a Gaussian surface, right? For a spherical case, for spheres, the Gaussian surface is also spherical, right? So this is our Gaussian surface. This is our Gaussian surface, right? GS. GS means Gaussian surface, right? And whatever the calculation will be doing here, it will be done on this Gaussian surface, right? It will be done on this Gaussian surface, right? Let's suppose this Gaussian surface is of radius small r. It's of radius small r, right? So applying Gaussian's law, that's E integral of E dot ds, that's equal to charge enclosed upon the epsilon naught, right? Since this is a hollow sphere, this is a hollow sphere, so the charge enclosed because of the hollow sphere will be equal to 0. So charge enclosed within the hollow sphere is equal to 0, right? And the direction of electric field, let's suppose, will be in this direction, right? ER cap, right? And the direction of surface vector is also along this. So we'll be doing, so it will be like integral of ER cap dot ds R cap, right? The charge enclosed is 0, so it will be 0 here. So R cap dot R cap will be 1. So E will come out of this integral, so will be integral of ds, that's equal to 0. Or we can say the electric field E inside is equal to 0. It means that inside a hollow sphere, if the charge plus Q is distributed on the surface of a sphere and the charge uh, inside the sphere is 0, it means that if this is a hollow sphere, there's no charge distribution inside the sphere, then the electric field inside the sphere is going to be 0, right? So the electric field inside a hollow sphere is always equal to 0, correct? So let's try to calculate the electric field due to this hollow sphere outside this sphere, right? Let's suppose that once again the same charge distribution is there, right? This is the charge plus Q. And we have to find the electric field at some point outside this Gaussian surface, right? Outside this sphere, right? Which is the radius R. So what we'll be doing is that we'll be drawing a Gaussian surface. Let's draw a Gaussian surface. So this is our Gaussian surface, right? This is our Gaussian surface. And the radius of this Gaussian surface is equal to r. On this Gaussian surface, the electric field intensity, the magnitude of the electric field intensity will be same at every point. And let's suppose this electric field is directed, it will be directed along the radius, or it will be away from the radius, or it will be directed radially outwards, right? So the direction of this electric field, E vector, it will be nothing. Let's suppose E is the magnitude of this vector and r cap is the direction of this vector, right? And the direction of this Gaussian surface is also along the direction of r cap, right? We can write it as ds r cap, correct? We can write it as ds r cap. So using Gauss law, once again, using Gauss law, integral of E dot ds, that will be equal to charge enclosed, q enclosed upon the epsilon naught, right? Q enclosed upon the epsilon naught, right? So if the charge enclosed is q, then the flux will be q upon epsilon naught, right? Let's suppose that this electric field has the magnitude E and it's directed radially outwards in the r cap direction. So integral of E, we can write E as E r cap, right? Dot ds r cap. That's charge enclosed upon the epsilon naught. R cap dot r cap will be once again equal to 1. So we'll be left with EDS, right? And E is a constant on the Gaussian surface, right? On the Gaussian surface, the value of E is constant. It's a constant magnitude, right? We can take it outside of integral, right? We can take it outside the integral. Taking E outside the integral, we'll be left with integral of ds, that's charge enclosed upon epsilon naught, right? So the total surface area of this sphere, of this Gaussian surface will be nothing. It will be 4 pi r square, where r is the radius of the Gaussian surface, right? So that will be equal to q enclosed upon the epsilon naught. From here, the magnitude E will be nothing. It will be equal to q enclosed upon 4 pi epsilon naught r square, right? So this is the electric field strength at a distance of r outside this hollow sphere. This is the electric field strength, right? Q enclosed upon 4 pi epsilon naught r. We know within this Gaussian surface, the total charge enclosed is the total charge on this sphere, right? That's the plus q. Plus q is the total charge on this sphere, and this is the same charge which is enclosed by this Gaussian surface, right? So q enclosed is nothing. It's equal to plus q. So q enclosed is nothing. It's equal to plus q. We can replace this q enclosed with this. So it will be plus q upon 4 pi epsilon naught r square, right? So this is the electric field intensity or electric field strength at a distance r, at a distance of small r outside this sphere, which has the charge distribution of plus q, right? The charge distribution is plus q. So in general, this is the electric field intensity due to spherical symmetry, right? For any charge distribution, that's q enclosed upon 4 pi epsilon naught r square. For this particular case, the total charge enclosed was q upon 4 pi epsilon. The total charge was plus q, so the electric field intensity is q upon 4 pi epsilon naught r square, right? So inside the hollow sphere, the electric field intensity is 0 because of the Gauss law, right? We'll try to find the electric field due to infinite line charge. Due to infinite line charge of charge density lambda, of charge density lambda, right? So if we have an infinite line charge distribution like this, so this is our infinite line charge distribution. It extends to infinity in the positive y direction, right? And it also extends to infinity in the negative y direction, right? It's a positively charged line charge, right? So it will be having a positive charge like this. The charge density of this line is nothing, it's lambda. That's the linear charge density. Right? So we'll be using Gauss law to find the electric field intensity at some distance r perpendicular to this line charge density. What we'll be doing is that we'll be drawing a Gauss law. We'll be drawing the Gaussian surface for this line charge density, and the symmetric surface or the Gaussian surface for this line charge density will be cylindrical in nature, right? So we'll be drawing a cylinder. So this is the Gaussian surface for this infinite line charge density, right? Correct? We cannot use sphere here, right? Because if we use a sphere here, then the magnitude or the intensity on the surface of the sphere will be different at different points, right? It's the only cylinder in this case which will give us the same electric field strength on the surface of the cylinder, right? Otherwise, if we use this sphere as the Gaussian surface, then that will not be symmetrical, right? There will be different electric field intensity at different points on the surface. So we'll not be using spherical Gaussian surface for this infinite line charge density, right? And let's suppose the radius of this cylinder here is that's equal to small r, and suppose that length of this cylinder is equal to L. That's the capital L. And we know that electric field will be directed in this direction like this because of this line charge density. And here it will be like this. And in case of cylinder, we know there are three surfaces. One surface is the covered surface area, and there is a circular top surface and the circular bottom surface, right? Let me call this circular top surface as S1, and let me call this as uh, S2, that's the covered surface area, right? Covered surface. And the circular bottom area, that's S3, right? You can clearly see that here there is no electric field light which is passing through S1 and S3, right? Or we can say that the electric field is perpendicular to the S1 vector and the S2 vector. So there will be no electric flux through S1 surface and S3 surface, right? You can say that phi S1 will be equal to phi S3, that will be equal to 0 because integral of E dot ds for these surfaces, integral of E dot ds for these surfaces will be equal to 0 because the angle between E vector and ds vector in these two cases will be equal to 90 degree, and we know that cos 90 degree is equal to 0, right? So the flux will be 0. It means that if this is our ds area, right? Ds area. So this ds area will be directed in this direction, eta cap, and our electric field is directed perpendicular to this surface, right? Perpendicular to this unit vector. We can say that the angle between this eta cap and the electric field vector is equal to 90 degree, or we can say that there will be no electric flux, electric field lines which will be passing through S1 and S3. So the whole flux because of this infinite line charge density will be passing through covered surface area, right? The total phi net will be equal to phi S1 plus phi S2 plus phi S3, right? These two will go to 0, right? And you'll be left with phi net that's equal to phi s2, right? We can see that in this case, if we draw this ds vector here, this is our ds, right? And the direction of this ds vector will be along this. That's, let's suppose ds eta cap is the direction, right? And the electric field vector is also directed along the same direction, or we can say that angle between eta vector and e vector here is equal to 0, right? So the angle between the surface area vector and the electric field vector here is 0. So we can say that phi s2 will be nothing. It will be integral of e vector dot ds vector, that is integral of e ds cos of 0, right? And the electric field on the Gaussian surface is a constant, right? I mean, by magnitude, electric field is a constant on the Gaussian surface, right? So it will be cos 0 is 1 integral of ds, right? So integral of ds will give us the total surface area of this total curved surface or area of this Gaussian surface, which is slender, right? And the curved surface area of slender is nothing. It's 2 pi r into length of the cylinder. So it will be 2 pi rl. So phi total is nothing. It's E times 2 pi rl. That will be called charge enclosed upon the epsilon naught, right? We know that lambda is nothing, is the q upon l. That's the charge per unit length, right? Charge per unit length. So this is the lambda, right? Or we can replace the charge here. That's equal to lambda times L, right? The charge enclosed is nothing. That's lambda times L, right? In this case. So we can replace Q enclosed with lambda times L. So we'll be left with E times 2 pi RL lambda L upon epsilon naught. So L and L will get cancelled. So E will be nothing. That will be equal to lambda upon 2 pi epsilon naught R. So this is the electric field strength due to infinite line charge at a distance of r. This is the electric field strength due to infinite line charge at a distance of r. So this is the electric field strength due to so this is the electric field strength due to the infinite line charge density at a distance of r, right? So our E comes out to be, E is nothing, that's equal to lambda upon 2 pi epsilon naught r, right? Where r is the distance, perpendicular distance from the line charge, right? So it means that if this is the infinite line charge distribution here, plus infinity to minus infinity at a distance of r, we have to find the electric field intensity. That's nothing, that's lambda upon 2 pi epsilon naught r, right? Correct? So we can rewrite it as, let's suppose we multiply it by 2 in the numerator and 2 in the denominator, it will be 4 pi epsilon naught r. And for 1 upon 4 pi epsilon naught is nothing, it's our k. So it will be twice k lambda upon r, right? So this is the electric field intensity due to the infinite line charge density at a distance of r. Let's try to find electric field intensity due to the infinite sheet. Electric field intensity electric field due to thin infinite sheet. Thin infinite sheet. It's a thin infinite sheet and also non-conducting, right? Non-conducting. Let me draw a thin infinite sheet, right? Let's suppose this is our infinite sheet, thin infinite sheet like this. It goes infinity, right? In all the directions. It goes to infinity in all the directions, right? And let's suppose the charge of this, the charge density on this sheet is equal to sigma, right? Sigma is nothing, is the charge per unit area, right? Sigma is the charge density, right? So sigma is the charge density, right? And it's a positive charge, right? So this positive charge is distributed on the surface of this thin infinite sheet like this. We have to calculate the electric field intensity because of this sheet, right? What we'll be doing is that we'll be drawing a Gaussian surface, right? We'll be drawing a Gaussian surface. And the Gaussian surface for this sheet will be nothing. It will be a cylinder. It will be once again a cylinder. So let's suppose this is the cylinder through this infinite sheet, right? So this is the cylinder through this infinite sheet. And let's suppose the electric field due to this infinite sheet will be directed along this direction, right? Like this, like this. These will be the electric field lines, E vector, correct? And let me suppose that the area of this circular portion is A and the area of this circular portion is A here also, right? And we can see that here also no electric field line actually passes through the curved surface area of this cylinder. So phi through curved surface area, phi through curved surface is equal to 0 for this Gaussian surface, which is cylindrical here, right? The flux or the electric field lines are only passing through circular portion of this cylinder, right? So the flux will be contributed by only these two circular portions of this Gaussian cylinder, right? So we can write here phi net will be equal to, that's the flux because of this circular portion here, right? Let me call the electric field is E here, and the direction of this electric field here in this case, direction of electric field in both the cases is along the direction of the area vector, right? In both the cases, the direction of the electric field vector is along the direction of the area vector. It means that angle between the area vector and electric field vector for this surface area and for this surface area is equal to 0 degree. Means the flux through these areas will be nothing. It will be E into A plus E into A, right? That's nothing. That will be equal to charge enclosed upon the epsilon naught, right? Charge enclosed upon the epsilon naught, right? So total flux will be twice EA. That's the charge enclosed by this Gaussian cylinder, right? Or we can say that E is nothing. It's Q enclosed upon twice A epsilon naught, right? Correct? Twice A epsilon naught. Where A is nothing. It's the area of cross section of this cylindrical portion, right? And this charge enclosed upon A, that's nothing. It's equal to charge density charge density, right? Which is uniform here, or that's equal to sigma, right? That's equal to sigma. So we can replace this q upon q epsilon naught upon a by sigma. So the strength of electric field will be nothing. That will be equal to sigma upon 2s epsilon naught, right? That will be equal to sigma upon 2s epsilon naught. So we can see here that for infinite sheet, if the sigma here is a constant, epsilon naught here is a constant, right? For the infinite sheet, you can see that electric field vector is a constant here, right? Electric field vector is a constant on both the surface, both the sides. Or we can say that electric field due to infinite sheet, it's a source of uniform field, right? It's a source of uniform field. Electric field due to this thin infinite non-conducting sheet, we can say it provides us a uniform electric field, right? Irrespective of the position of the distance, right? It does not depend upon distance. For all distances, the field is constant, that is sigma upon 2 epsilon naught, right? Let's suppose that if we have two non-conducting sheets here, right? One is having plus sigma charge and another is having minus sigma charge, right? These are infinite non-conducting sheets, one with plus sigma charge, another with minus sigma charge, right? We have to calculate the electric field intensity in this region. Because of this plus sigma, the electric field will be directed along this direction. It will be away from this positive charge. And because of this negative sheet also, the electric field intensity will be towards this negative charge, right? So let me call this as E1 and let me call this as E2. And E1 is nothing, that's equal to sigma upon 2 epsilon naught. And E2 is also equal to sigma upon 2 epsilon naught, right? So the total electric field, that's equal to E1 plus E2 because both the fields are directed along the same direction. So it will be twice sigma upon 2 epsilon naught, but that's equal to sigma upon epsilon naught, right? Correct. That's the region between these two surfaces. Let me call this P, let me call this A, let me call this as C, right? In this region, in region A, if we have to calculate the field in region A, because of this plus sigma, the field will be directed along this direction, that is sigma upon epsilon naught, right? Sigma upon 2 epsilon naught. And because of this negative sheet here, the field in this region will be directed once again along the negative sheet. So that will be sigma upon 2 epsilon naught, right? Sigma upon 2 epsilon naught. So in this region, the net field E net is going to be 0, right? E net is going to be 0. And similarly, in this region also, the E net is going to be 0. So E net is going to be 0 in this region also. So if we have two thin non-conducting sheets, each of charge density plus sigma and another with a charge density minus sigma, then in between the regions of two plates, the electric field will be 0. There will be no electric field, and outside the electric field between the sheets will be sigma upon epsilon naught, and outside the sheets, outside these two sheets in region A and in region C, the electric field will be equal to 0, or the net intensity of the electric field vector will be 0 in these cases. So it means that if we place a charge q, external charge q in region A and region C, it will experience 0 force, or we can say it will not experience any electrostatic force, right? So we can stop here, and in the next class we'll be discussing with the electric field intensity calculation because of the non-conducting sphere inside as well as outside of the sphere, right? So that's it for today. Take care and bye bye.